of the sight glass, you'll see a colored dot in there. And on the outside of the sight glass, there'll be corresponding colors that'll tell you if it's this color, it's wet, which means it has moisture in the system. If it's another color, it's dry, which means it's good. That sight glass, you can actually see the refrigerant as a liquid form flowing through that sight glass. Even though it's liquid, you would think it would say it's wet all the time, but their wet is just looking for moisture in that refrigerant. They're not looking for a liquid or a gas form. They're using moisture as being wet. A crankcase heater is often used to prevent refrigerant from migrating to the oil during periods of low ambient temperature. Refrigerants in the oil will cause foaming in the compressor at startup. So that one doesn't have it, but that big compressor sitting there, I think the heater's still in there on the bottom of that crankcase.
It's still there.
I think it's just blue wires coming out. There's a heater.
Black wires coming up.
It's black wires?
Yeah.
There's a heater that slides in there. It's about 4 inches long, ½ inch around. That heater lays right in the crankcase and just keeps that oil hot in there. As long as that oil's hot, the refrigerant will boil off, turn to a vapor, and be out of the oil. When that's not working and it's cold outside, refrigerant will migrate to that oil, set in there in a liquid form. As soon as you start it up, you'll fill that whole crankcase up with foam. And it pushes the oil out of the system. It's just foam in there. So that's why a lot of your heat pumps, residential and the larger systems, almost all commercial, have crankcase heaters, and they tell you to energize that crankcase heater at least 12 hours before you're going to do a startup of that equipment. So if you come out and install a new piece of equipment, you get it all ready, you disconnect the contactor for the compressor so that you can't start your compressor, turn the power on, and just let that heater sit there and heat up all night long, get all that oil hot and all the refrigerant out of the oil, so the next morning when you come in to start it up and put it in service, it's ready to go.
Not only that, it's easier for the start up anyway.
Yeah.
The compressor itself.
When evacuating a vapor compression system, the vacuum pump should be capable of pulling 500 microns, which is 29.9 inches of mercury. Just because your gauge says you're at 29 inches of mercury doesn't mean you're at 500 microns. Microns start out, atmospheric pressure is 740,000 microns is atmospheric pressure. You put your pump on there, and within 30 seconds, your pump says you're at 29 inches of mercury. You didn't pull it down from 700,000 to 500 in 30 seconds. You know, it'll pull down, it'll take it probably 45, 50 minutes to even get down into a 1,500, 2,000 micron range. And then probably another hour or so to get from that down to 500 microns. So just because it says, 29 inches of mercury is a perfect vacuum, or it's not a perfect vacuum, but is as high as you can attain. Put your micron gauge on there, pull it down to 500 microns, and that ensures that you have a clean, moisture-free system, and it's sealed tight. If you got the smallest pinhole leak, you'll never get 500 microns. The best you'll get is maybe 1,000. And that's, a tiny little pinhole leak. It just won't pull down. Warning, a hermetic compressor's motor windings could be damaged if energizing the system under a deep vacuum. Whenever we're doing installs, I always, when we're pulling vacuums, we always lock out the disconnect, just so that it can't inadvertently get turned on, or someone try to bump a compressor to make sure that rotation's right or whatever. Because when you got it down into a deep vacuum, you can burn the windings up on a compressor pretty quick just by bumping it over. So always make sure that the lever is turned on. The use of a large vacuum pump can cause trapped water to freeze. Now they're talking about it in a chiller. Mainly when you're pulling a vacuum on a chiller, it uses condensed water to run through the barrel. Your water is what's absorbing the heat out of your refrigerant. Your refrigerant's on outside the barrel, the water's inside the barrel, and it's transferring the heat that way. If you're pulling a vacuum on a chiller, you're dealing with hundreds of pounds of refrigerant, and you use a really large vacuum pump. If you don't get that barrel completely drained out or flow water through it all the time while you're pulling a vacuum, you freeze the water up inside that barrel and crack and bust it.
You use a regular vacuum like you got there, or
Like that little vacuum pump? You can use them, but it'll take you forever. They have large commercial vacuum pumps for chillers.
okay.
I mean, like that little one there, I think is probably a 5 CFM, pulls 5 cubic feet of air per minute. The large ones, they've got 25 and 30 CFM pumps.
Okay.
That will, and then the line on those pumps are probably an inch and a half diameter line that they use, so they can pull them down. But when you're pulling that refrigerant, you're vaporizing that refrigerant that fast, it drops off real quick and flashes off, and it can actually freeze up any residual water in that condenser barrel. So they either make sure you drain them out completely, or just turn your condenser water pumps on and always have it flow, have water flowing through that barrel. As long as it's flowing, it's not going to freeze. It says there is a risk of freezing. When there is a risk of freezing, liquid charge of an R12 refrigerant system should begin with vapor from a vacuum level to a pressure of approximately 33 psi, followed by a liquid charge through the liquid line service valve. This is also the proper method for charging a system that contains large quantities of refrigerant. Not so much even R12 anymore, even the newer refrigerants. When you're dealing with anything that has water as for its condenser, and you have water in a barrel or water in a tube-and-tube heat exchanger or whatever, when you're charging that up for the first time, bring it up to 33 pounds of pressure with vapor. You don't want to dump liquid into it, because you're dumping the liquid in there, and then that liquid's vaporizing off, and as it's turning to a vapor, it's getting really cold, and you can freeze up the tube-and-tube cylinder just by dumping the liquid into it. Gets tricky because we have some 410 systems that I'm using right now, 410 heat pump, geothermal heat pumps. You can't put 410 in as a vapor. Tells you not to, because of fractionation. It comes out of the tank at a different rate. So they make a special tool. I think there might be one in here. I thought I'd seen one in the case here, that you put it on your tank, and it brings it out as a liquid, but turns it to a vapor as soon as it hits the hose. So you can charge liquid.
Most of the time, they want you to charge it as a vapor anyway, through most systems, so you just won't plug the compressor.
Not 410, you gotta charge 410 as a liquid. That's where you use one of these. You screw this onto your tank, take it out from your tank upside down, hook your refrigerant hose onto here. It comes in here as a liquid, so it comes out of the tank as a liquid, which means it's coming out under ideal mixed conditions. And inside here, it flashes to a vapor. It comes out of here as a vapor. Once it gets in the system, it doesn't matter if it's a liquid or a vapor. It's going to do what it has to do. It's just getting it out of that tank as a liquid so that it's a pure blend of what it needs to be. You can use these. I'll pass this around. But I always tell my guys, if you don't have something like this, if you don't have that, you can take a regular hose set and you hook the line, the yellow line up to your tank, and hook the blue line up to your low side and the red up to your high side. Whenever you're charging it as a liquid, you just take this and you barely crack this thing open. And you're letting liquid come up into here, but you're using this point in here as a metering device. So it flashes off. It's all liquid right there, but it's being metered here. It's coming from a higher pressure to a lower pressure. So it's turned into a vapor. And it's all vapor then when it comes out here and goes into your system. If you open it wide open, you're dumping liquid right through it. But you just barely crack it open, just enough to get a metering system in here. And you can use this as a metering device. That's basically what that is. It's just a metering device in there. It's high pressure to low pressure, and it lets it vaporize off. Under safety, it says additional safety and shipping information is covered in the core section. We went over safety there. But ASHRAE Standard 15 requires a refrigerant sensor that will sound an alarm and automatically start a ventilation system in occupied equipment rooms where refrigerant will leak, where refrigerant from a leak will concentrate. So most of your large, commercial buildings that have a boiler room and a chiller room and all that, it's a refrigerant monitor system. It just constantly senses the air. And if it senses refrigerant in the air, sets off an alarm and turns on the exhaust fan and dumps everything out. Yeah.
None of the old ones.
None of the old ones. They're even becoming more and more, we'll get into them in here, with basically scuba apparatus. It's just like scuba gear. You got the tanks and the mask and everything, and they're usually stationed right outside the door. That if there's a leak, the little alarm is going off, the lights are flashing. You got to put that scuba gear on before you go into the room, just to try to determine where the leak is and maybe valve something off and stop it. But they don't want you going in there without some kind of protection, because refrigerant is heavier than air. If you walk into a room and you get a big gulp of that refrigerant and it gets into your lungs, it stays in your lungs and it displaces the oxygen. You have a hard time breathing. The more you get of it in there, the fuller your lungs are going to get. You're not going to get any air. You end up passing out and dying. There was a guy just a year or two ago at some building, I don't know where it's at, it was around here, that died from refrigerant exposure. He got too much of it, passed out in the room, and they didn't know it until it was too late. You need to know these categories: refrigerants CFC 12, CFC 11, and HCFC or HFC 134A are A1 refrigerants. That's definitely a question on there. They're categorized as an A1 refrigerants. All refrigerant systems must be protected by a pressure relief valve, and they cannot be installed in series. Now, this is type 2, so we're dealing with larger equipment. More type 1 systems don't have to have the 5 pound or less, don't have to have these pressure relief valves on them. You start to deal with larger refrigerants, you gotta have the relief valves. Pressure relief valves, when they're talking about in series, if you've got a high side liquid line here, going from, your evaporator to your condenser, right here, they'll put a T and put a pressure relief valve on it. You can have multiple pressure relief valves if you want. So if one fails, you gotta back up, and you gotta back up for that one. But you can't put this relief valve that way and then come up here and put another one here and another one here. That doesn't work. That's in series. This would have to fail, and then this one would have to fail, then this one would have to fail. So you'd have to have all three of them fail before it would vent out the top. You can put them one right after another. This one could fail and it would vent, and these two could be fine. So you can install them that way, but never install them one on top of another. Never energize a reciprocating compressor if the discharge service valve is closed. That's like that big compressor over there. The top valve, the top piece of pipe coming out is the discharge side. Pipe going into the side there is the suction. If that discharge on there is closed, don't ever start that thing up. You'll end up busting valves or crank rod or a piston or do something to it. Because those things, there's a lot of power there and there's nowhere to push that refrigerant. You'll end up busting something. And then we get into more stuff here. Type 2 certifications for technicians who maintain, we've already done that. Leak repair requirements. All of the recovery requirements under type 1 apply. Please refer to page 2. Okay. Recovery equipment classification. Active or passive. Active is self-contained. It uses its own means to draw refrigerant out of the refrigerant system. It's using the compressor. It's using its own compressor. That's an active or self-contained. System dependent. It uses a recovery machine. It relies on the compressor, an appliance, and or the pressure of the refrigerant and the application to remove the refrigerant to an external container. I'm sorry, I told you wrong. Self-contained or active uses a recovery machine. It has its own means to draw the refrigerant out of the system. So, self-contained is a self-contained recovery machine. System dependent or passive is dependent on the compressor in the system. It's dependent on itself to get that refrigerant out of there. Here we got leak repair requirements.
On system, real quick, on system dependent, what about if the compressor is not working?
If the compressor doesn't work, you can go back where we was talking about using a non-pressurized container. You can heat the system up, and through heating it up, it'll push the refrigerant out. But you've got to be able to obtain certain vacuums, and if you can't, then you still have to hook your machine up to it. That's where system dependent is. I've never used it. I've never seen it done. I don't even think they really deal with it anymore. The EPA, they put it in there. Almost everybody now uses a recovery machine. It's just
you open
quicker.
the valve, let it dump whatever it can out, and then you go ahead and hook up the machine and jump it down and go out the way.
Yep. On leak repair requirements, you have more than 50 pounds of refrigerant, commercial and industrial process refrigeration. If you leak 35% or more of the charge annually, you have to repair it. If it's more than 50 pounds, other than commercial or industrial processing, which is just comfort, like a house, even an office building is comfort, air conditioning.
How do you tell if it's 35%, said annually, you're not gonna sit there with something posted up and.
Now, if you're 35%, if you have, you take the amount of refrigerant that it holds, say it holds 100 pounds, and the first time you come out, they're not looking for you to, the first time you come out, fix it if it's a little bit low. So you put refrigerant into it. If it holds 100 pounds, and you know you put 10 pounds of refrigerant in it, okay, you've only lost 10% of the charge. You come back out, and providing you're the contractor that's maintaining a service contract on it, you come back out next year, and it's lost a whole lot more. You know you gotta fix it. You know, next year you gotta put 40 pounds in it. Now you lost 40%.
That's all determined on whether you're the same provider of service.
Right. If you come out and the first time, it's a 100-pound system, and you gotta put 60 pounds into it to get it up, you should go ahead and repair it, because you know you're over the 35% leak rate.
I can't believe that the electric commercials go away with that much. That's a lot of refrigerant.
Yep.
A lot of refrigerant.
Yep. And then if you're less than 50 pounds, there is nothing you don't have to fix it. If it's a less than a 50-pound charge. Doesn't matter if it's commercial, industrial, comfort, or whatever. It says it's not good service practice, it should be repaired,
Yes.
but by the EPA standards, you don't have to repair it.
That's what I don't understand. It should be all the same, right across the board.
ADS?
Because the complex gets smaller as the amount of freon needed gets lowered, or
Not
repairs.
No.
necessarily.
No. It's not any harder to repair
Yeah.
something that has 5 pounds of refrigerant versus something that has 200 pounds of refrigerant.
Costs more because it's a bigger system.
Right, but it's really not any harder to find the leaks in one versus the other and fix it. Recovery requirements for small appliances. We've done better over this. Before November 15th, 1993, running or not, 80% or 4 inches. After November 1993, if it's not running, it's 80% or 4 inches. If it is running, it's 90% or 4 inches. I'll let you read that last page if you want. Here's kind of different places of where to recover. It says to recover refrigerant when the condenser is above the evaporator. First recover the liquid line entering the evaporator. So if you look on there, the top part, your condenser's up here, your receiver's up there, and your liquid line comes down here going into the evaporator. So you would recover at that point, right before your metering device. That's where you're gonna have the most liquid in the system. And
So
this,
you just put a piercing valve right there.
yep. And you really don't have to use piercing valves. I mean, they make nice tools now. It's kind of like a pair of vice grips that has a valve, has a piercing valve built right onto it with a nice little rubber seal. You clamp that vice grip on there and screw it tight, and it pierces. As soon as you squeeze it shut, it pierces. It has a Schrader valve on it. Hook your lines, hook your hose up to it, pull everything. When you're all done, pop it off. If you're just pulling that out to do a repair, pop them off and brace right over a nice little hole where you know it was there. You know, that's a whole lot
That's why
easier.
I've seen those before, but I've never used one of those.
Yeah, they're easier and better than those little bullet
Yes.
piercing valves that
Tighten them up a little.
yeah, you take over with an Allen wrench and strip them out because they're made out of real cheap pot metal.
Mhm.
Make it real too tight, and then they strip out. So they're a pain in the ass. And then here, if you're a receiver above condenser, to recover refrigerant when the receiver is above the condenser, recover from the condenser outlet, receiver outlet, and metering device into the evaporator inlet. So if your receiver is up higher than your condenser, typically you're pushing a bunch of liquid up into that receiver and storing it up in there. So you would recover at the bottom of your condenser, when it's coming out of your condenser, going to your receiver, recover as much refrigerant as you can there, then recover it down again at the, right before the metering device. You pull the rest of the liquid out there, and then you start here and just recover from the rest of the system. We'll get into a couple different techniques where you can recover liquid refrigerant. It's what they call a push-pull method. That system there, if you were just using that system to recover the refrigerant, you would have to recover it in a vapor form, because the compressor won't compress liquid. But you can take that machine and you hook that machine up to the vapor side of your recovery tank. So you pull vapor out of the tank into that there, and then you put the discharge side into the inlet of the condenser. So you're pushing vapor into that condenser, and then you take a hose right off of the outlet and go to back into your recovery tank. So you're using the equipment to push vapor into the system to push the liquid out through to your tank. That way you can recover a lot of liquid quicker. We call it a push-pull method. I probably didn't do a very good job of explaining it. But if you have a system here, this is your condenser, and it's going through the receiver, and then down to your coil, back up to your condenser. If you put your recovery machine down here and your refrigerant tank, on your tank you have two valves there. You got a high side and the low side, or liquid and vapor. If you have the inlet and the outlet on your recovery machine, if you take the outlet from here and push it here, outlet goes to there, you take the low side here and come into there, and then you come from here back to your tank. Now, the tank in here on the low side, you're drawing vapor here, out of here, it's drawing it up through your pump, pushing vapor into your system here. You got a bunch of liquid in here. If you're pushing vapor in here, you're gonna push all that liquid out through there and push liquid right back into your tank and fill your tank up with liquid. You do it a whole lot quicker. You can get a lot of the liquid out fast. Once you do that, then you can go back and pull it as a vapor. You get as much of the liquid out of the system as you can. Then you hook it up normal way and pull vapor.
Why would you, but you wouldn't do it the opposite on the tank though? I mean.
No, because you want this to be vapor. You don't want to be pulling liquid out of your tank.
Yeah, but on the high side, I thought we should do the vapor side though, of your tank.
Yeah, you would, no.
I mean, you would know better than me.
No, the high side is liquid. The red side is liquid on your,
Is it?
yeah.
I thought it was the other way around.
Pretty sure.
I-
We'll check and see. I'm pretty sure the high side is liquid on your recovery tank.
I'm not positive myself on it, so I've never been positive on it.
Yeah, I'm pretty sure the high side has the tube that comes down in, and the low side is just off of the top of the tank.
Okay.
Yep. But that's the method it's called a push-pull method. And there may be questions on the test about that too. And that pretty much covers the type 2. So a lot of type 1 carries over to type 2,
Yeah.
but some of type 2 goes further than type 1. That makes sense. For the percentages of what you gotta pull out, or the amount of vacuum you gotta achieve. Type 2 sometimes takes a little further than what type 1 does. So just study them and try to remember the tables and a lot of the requirements. Remember that 12, 11, and 134 are type A1 refrigerant. It's kind of nice. All right, guys.